Hello, everybody. Welcome to the TFA Tech Forum. Today, Rohit, Mathew from the Infra Solutions team in ARM will present the NUMA-aware PER-CPU framework for enhancing latency and storage efficiency. Yeah, over to you, Rohit.
Thank you, Olivia, and thank you all for joining in. So I'm Rohit, and I work for the team which develops firmware for the newest reference design platforms. And I'll be talking about NUMA-aware PER-CPU framework for today's call. Let me get my pointer. Yes. So look at the agenda for today's meeting. We'll start with a problem, the reason for why we need such a framework. And then we'll take a look at what the framework does. So we'll break it into different steps and see what the framework is. And the way we have organized this slide is by having a very simple design as we start off, and then taking a look at a couple of optimizations that can make the framework a bit more efficient and performant. Those have been separated out so that we understand the trade-offs in doing these things. Okay. Now, to start off, we'll focus on one specific segment of platform, which is the homogeneous multi-chip platform. So homogeneous yes.
Sorry, just when we talk about NUMA, right? It's not just about per CPU objects, right? There could be a hierarchy.
Yes.
When you guys say per CPU objects, right? There's if you think of higher level operating system NUMA, we have a concept of NUMA nodes, and there's going to be per node structures in addition to the per CPU structures. So I just want to make sure that we don't rule out that as well. Does that make sense?
That makes sense, but at least for this presentation for this particular framework, we're starting off with the per CPU objects. It can be expanded if there's a scope for expanding it to other nodes, like you said, probably higher up the hierarchy where we have Linux, we have many other things which are part of the NUMA domain. But for this presentation, we'll be focusing on the per CPU objects. Does that answer the question?
It does, but I think there's a problem with developing frameworks without having a full set of requirements. We'll go through it today.
Okay.
But I think if you have the problem here, and we could talk about requirements and as well. It'd be nice to make sure we have a list of requirements so that we could check the framework against.
Okay.
Does the framework meet the requirements or not? Sure. We can continue.
Sure. Thank you. So taking a look at the problem, if we think of homogeneous multi-chip platforms, we have essentially chiplets which are cloned across different in multiple numbers. So let's say if we have a quad.
Sorry, Rohit. I'm just wondering, is it just me or everybody is seeing that the presentation is not in a good format? I mean, it's going out of the screen.
Is that
it looks fine for me?
It looks all right for me.
Okay, then. Sorry.
Okay.
It feels zoomed in to me. But...
Okay. So is it okay to proceed, or?
I'm seeing the presentation okay. I hope it will record it properly.
Yeah,
Okay,
continue, Rohit.
Okay,
continue.
I'm hoping it's fine for everyone then. Yes.
Yeah.
Yes. So the problem is we have similar chiplets in multiple numbers, and they have segregated SRAM, so they can be discontinuous in the PA space. And the way we have trusted firmware software designed currently is that we place it in one SRAM, and then the other SRAMs don't have the runtime image, and then we see with the scaling happening, with number of CPUs getting more and more, the image size gets bigger. So the question there is, can we reduce the runtime image size on the primary SRAM, assuming that's where the image lies? The next question is obviously what we just touched upon. That's any sort of cross-chip access would have a NUMA latency, and then can we have parts of whatever parts we can move across? Can we have them in the chiplet in context for the CPU in execution so that the NUMA latency is low? Now, with these two problems, we'll take a look at one class of objects, which is the per-CPU objects, and see how they face these problems. So TFA has a lot of global objects, which are per-CPU. RMM context is one of them. Non-secure PSCI context, SPMD context, etc. So there are many more, and they're all part of the BSS. So they're not explicitly loaded, but they're still part of the runtime image. And most of them stay through the lifetime of the system. And what that means is that any time there's an access from a CPU which is not in the chiplet where we have this stored, there's going to be a latency. And the storage problem, if we think of this as the SRAM where the image is loaded, and this as a runtime image, so we have the proc bits or the loaded sections and the no bits or the sections which are not loaded. BSS is going to grow as CPUs grow in number. The stack is also going to grow. And then there'll be a bottleneck at some point where the image is quite big for the SRAM to hold. That's where we propose this solution where we have a NUMA-aware PER-CPU framework. And
Sorry,
what
Rohit, just on the previous slide, I think it's worth clarifying. So the SRAM, what is being represented here is for one chiplet. And currently, as TFA as it stands today, we need a contiguous block of SRAM for TFA to run and execute. In a multi-chiplet platform, you have SRAM distributed across the address space, and hence, although we would not be able to fit the entire TFA image in one particular SRAM of one chiplet, across the different SRAMs, it would be possible to fit TFA. So what the solution, what Rohit is proposing is kind of allowing TFA to run across these multiple SRAMs across multiple chiplets. Yeah, thought it's just worth clarifying.
Yeah, sure. Thank you, Sobi, for that. I do have a slide where there's a better picture of how SRAMs would look with the multi-chip case, so probably a couple of slides down. But thank you for adding that. And yeah, so coming back, that's where we propose this framework. And what it would do is, it is like any other per-CPU framework, but it also supports NUMA allocation, which means that underneath the framework for multi-chip systems, it is going to spread out the allocations on different chiplets. And we have two aspects to it. One is the definer interface, then the other is the accessor interface. So definer interface is the interface that we use for defining any variable, any objects, any per-CPU object. An accessor interface would be likewise used for accessing these objects. Now, there are some statements that are said here. For example, single chiplets won't have any change, but there is a star next to it which says that depending on how much of optimizations we plan to take in, there could be changes. But for the simple design that we think of initially, let's assume that single chiplets won't have any change, but multi-chiplet systems would have, obviously it would have changes for making sure that the allocation is spread across SRAMs. For the yes.
Why the focus? We have multi-socket systems, right? That this isn't a new problem with chiplets, right? I think that's part of that assumption. I think is a problem. NUMA awareness is not just a chiplet problem; it's a multi-socket problem, right?
Yes.
So we shouldn't constrain ourselves to thinking about chiplets because NUMA concepts already exist. There are ARM products out there that support NUMA already. And, ideally you want the framework to be generalized so that it's not focused on chiplet hierarchies, could be socket hierarchies as well. So it'd be good to just make sure we generalize it as NUMA nodes, whether it's a chiplet or a socket or something else.
Yes.
They're just NUMA nodes, right?
Yeah, I agree. I agree to that completely. Yes, I think it might be better to call them as NUMA nodes rather than chiplets. So chiplet is just one of the example, like you said. Socket can be another case. That's true. Okay, so continuing with what we said for just for this presentation, I had this as multi-chiplet. So multi-chiplet systems, we would have a separate section that's called per-CPU, and that'll tie all the objects within that section and just duplicate it across different SRAMs. So this is the slide I was talking about, where we have view of how things could be different. Now, for a single chip case, there's not much of a change. So we have the proc bits and the load bits, and there's nothing really changing. But for the multi-chiplet case, or the case where we have the NUMA coming in, assuming this is the first chiplet or the first NUMA node, and this is the second NUMA node, what would happen is we have a different section now for tying the nodes. So it's called the per-CPU section. And it will have the per-CPU variables for the CPUs that are part of this node. So that will be the idea. So the load is naturally going to reduce. Instead of having, let's say, if we had 16 CPUs for the entire system, it is going to have 8, 8. If the division is 8 and 8 across 2 nodes, it'll be just 8 nodes for this particular section, and the other SRAM would also have a similar section, and that will have the other 8 nodes. So that's how we divide it. And now this is local to this particular node. This section is local to this particular node. Accesses don't have that latency, and the storage also is going to reduce with that. So that's how it looks from a visual perspective on a multi chiplet system or chiplet where we have multiple NUMA nodes. Coming to the software aspect, what has to be done with respect to platform? We'll start with the platform. So the way we have this slide is, at least for the next few slides, we'll have single chiplet or the non-NUMA case, and what will be there for the NUMA case where we have more than one NUMA. So in this case, single chip, we don't really do anything. Nothing has to be done. But at least from a platform perspective, for the case where we have multi-NUMA nodes, we have to set a flag called per-CPU multi-chip, or we'll probably rename it based on the feedback. It's basically saying that we need NUMA allocation. It has to be spread across different SRAMs. So that's one thing. The second thing is, going back to the slide, this is the region where we want to place the per-CPU section for the other NUMA nodes. Is completely up to the platform. So the platform has to set up the page tables. So that's one of the responsibilities for the platform. The other responsibility is implement a function which would return the base address for that particular section. So this would be used for the computation of where a particular per-CPU object is during the access time. So this is this is for the platform to implement, and then the common framework would make use of this function as we try to utilize this model. That's the platform's responsibility. Obviously, there's also an aspect which I have not touched upon. The BSS has to be cleared out because this is part of a no-load section. This has to be zero padded. But the framework would make sure we do that. It is just the platform's responsibility to call the right APIs during the early architecture setup. So coming to the definer interface, now this is how we make use of the framework. So the first part is how do we define a per-CPU object? So the interface is like this. We use define per-CPU, then there's a type, then there's a name. As an example, if we use RMMD context, we use this. This will probably be the way we use this particular interface. And underneath it, for single chip, it's essentially same. We're not doing anything. So it's type, name, and then there's platform core count. So that's not going to change. But with multi-chip, we do have a difference where it becomes chiplet count. So the CPU count has come down because it is just for the chiplet or just for the NUMA node. And it is tied to a particular section. That's a section we talked about earlier, which is called the per-CPU section. Accessor interface. So one of the accessor interface is the for CPU variant. What I've shown here is the for CPU pointer, which would return a pointer for a particular CPU's per-CPU object. The way we use it is we use the name of the object that we want to access and then the CPU. And for single chip, all it's going to do is it's going to return the address of that particular CPU's object. Now, the use case is as follows, where we have per-CPU pointer RMM context, which is the name of the object. And then assuming this is the CPU number, we're going to get a pointer to RMM context for that particular CPU that we have passed on. Multi-chip, similar interface. Obviously, the interfaces are all similar in terms of how they are used. Implementation is going to differ. And what we do here is we try to get, based on the CPU, we try to understand what NUMA node it is. And for that NUMA node, we get the base address, which is again something that a platform would return to us. Like I said, there's a platform's responsibility to implement this function. And then there's a bit of computation to find out what CPU is the one in picture. So what is the offset of the CPU from this particular base? So that's how we return the address for the multi-chip or the NUMA node case. Just want to highlight that we're talking about a case where the platform implements a particular function called plat per-CPU section base. There's a better way to do it using TPIDREL3. We'll touch that in the optimizations, but at least for the simple design, we think of it as a case where the platform is going to return back the address for the section where we place the per-CPU for NUMA nodes. Similar to the for CPU interface, we have the this CPU interface. So here it is the CPU pointer, which will return a pointer for it will return a pointer for the CPU in context, the per CPU variable for the CPU in context. So the way we use it is the CPU pointer and name, and internally pick up the CPU which is executing currently, and then it will return the address for that particular object. Again, single chip doesn't have any change. Multi-chip, very similar in how we do things compared to the for CPU interface, and it'll return a pointer. So this is an example where we have RMM context, the CPU pointer, return a pointer for this particular CPU's RMM context object. Yeah. So coming to the optimization, the first optimization that we have is using TPIDREL3. Now, taking a look at, let's say, for CPUs, multi-chip implementation, what happens is there's a platform call, and then there's a bunch of computation that we do, which would finally look like something like this in disassembly. So there's this call to get the core position, and then there's the section base that has to be implemented by the platform. So there's already a branch, and then we calculate how the core position has to be made, and then there's another branch to get the base address. So it's a bit intense in terms of what it does. We can optimize this to something as simple as this. So the idea is that TPIDREL3 would store the offset. Since it's a system register and therefore every CPU, the idea is that TPIDREL3 stores the offset for a particular CPU. So we don't have to get the base and then compute the offset for a CPU, but rather we have TPIDREL3 itself pointing to that offset. And it's just a matter of adding that offset for the particular variable. So every CPU would have all its variables in stacked in position, and so it's just adding that offset. So it's just two operations. It's as fast as it can be. Now, there's a catch to it. As of now, there's a CPU data object that is making use of TPIDREL3. So if we want to make use of TPIDREL3, the idea would be to make CPU data object part of the framework, free TPIDREL3, and then utilize TPIDREL3 for the framework as such. So that has to be a change. That has to be that change that has to come about for getting this optimization in place. But it's a very good optimization to have. It'll be much more faster in terms of if we are to use this calls multiple times, it is much more faster. So that's the idea. And these points just talk about what I just said. It is even faster than a cached pointer, because a cached pointer miss would in turn go back to memory, but this is just a system register access. So that's the other thing. The optimization, the second optimization that I'd like to talk about is avoiding cache thrashing. So it's a very interesting phenomenon whereby currently we have all the per-CPU objects that we talked about, RMM context or SPMD context. These are all defined in this fashion, where we have type, name, and then it's an array of CPUs. So if we have 16 CPUs, it's just contiguous 16 objects in memory. Now, what happens is this can lead to fault sharing, or what we call as cache thrashing, where the ownership of a cache line keeps switching between CPUs. So I have a small animation of what is happening. So assuming this this is one cache line. D1, D2, D3, D4 is one cache line. And D1 is the per-CPU object for CPU1, D2 is the per-CPU object for CPU2, and D3 is the per-CPU object for CPU3. What would happen if all these CPUs would want to modify it sequentially? So to start off, CPU1 sends a request to the interconnect to fetch the cache line, and the interconnect sends it to memory. This is picked up in the local cache for CPU1. CPU1 modifies it. So now D1 is changed to what it was in memory earlier. Now CPU2 wants to modify its per-CPU object. Now what happens? It sends a request to the interconnect. Interconnect is clever enough to know that the cache line is with CPU1, so it sends a request to CPU1. This would lead to CPU1 invalidating its cache line because this is going to be a modification. It is going to be a write that has to happen from CPU2, and the interconnect passes the dirty cache line to CPU2. Now CPU2 modifies it, and it is having the ownership of the cache line. And CPU3 now wants to modify its per-CPU object. So the same thing happens. It sends a request to interconnect. Interconnect sends the request back to CPU2. CPU2 forwards it to CPU3. So now the dirty cache line is with CPU3, and CPU3 modifies it. So think of a case where we have hundreds of CPUs, and what would happen is if we have to sequentially modify it, or if we have a case where cache line is shared, the cache line keeps switching between CPUs, and this is something we want to avoid. What could
do
be
we have examples, Rohit?
Yes.
So most per-CPU structures are large enough that they fit in a cache line, and I thought we're already cache line aligned. Is there an example of a CPU structure today that is not cache line aligned? Like the context structure, for example. So I think we align those on the cache line.
So even if we align it on a cache line, let's assume it is aligned on a cache line. What would happen is the object for CPU1 might not be aligned because it is a contiguous array, right? The start address is aligned to a cache line boundary, but what would happen is CPU1 could very well fall off the cache line. So for an array, it is just that it is contiguous in space. So CPU1, CPU2, and up till CPU-n can very well fall off a cache line. And even if it is bigger than a cache line, it can fall between a cache line. That could happen. So that's still a problem.
Yeah, so some of the performance critical data structures have already, they are already aligned to cache line sizes. So the entire, both the start and the end address are aligned to the cache line, so they fit in a cache line. Now, because extra padding has to be added to these data structures so that they can align to the cache line, it costs memory. So there's a trade-off here. Memory, we need to spend memory to align them to the cache line sizes. So we don't tend to align all the per-CPU structures, but the most performance critical ones are already aligned. But yeah, your framework should automatically take care, because once we add these per-CPU data to your framework, and because the firmware, this framework is applying globally alignment on a particular CPU's object, we should get cache line alignment, but without much loss in padding.
Got it. So there are okay. There might be some structures that fall into this cache thrashing category. They're probably ones that we access less often, but and this just yeah, I got it. We're solving the problem altogether by divvying up the contiguity requirement becomes a per CPU object requirement rather than a structure requirement. Got it.
Yeah.
Yes. And the way we solve it is, so there's a slight modification in how we define or how we implement our framework now. So rather than having an array, we make it type and name. So there's no array anymore. So it is broken down, and then all the objects are placed together. So that's a linker script change where we place it on a cache line boundary in a per CPU fashion. So how it will look is CPU 0 would have all its object together. It will be on a CLA boundary. It will be on a cache line aligned boundary. And before CPU 1 starts off, it is again on a CLA boundary. So what the advantage here is that for the case where we were looking at with the cache lines moving across CPUs, CPU 0 can very well keep the cache line in its ownership, and CPU 1 can in parallel modify its data. So there's no problem with cache line sharing at all. If you break the array, the contiguity is a problem. If you break contiguity, make CPU specific data for a particular CPU together, so that all CPUs are separated out. So that's optimization 2. Now this is just stating what we saw. So the idea is that problem of cache thrashing comes up with contiguity. So extra cache line alignment along with breaking down the array could solve this problem. We club all CPU objects together, we sort them by alignment, and we place them on a cache line boundary. This could take a bit of storage. It depends. It could. That's why could is in italics. It could take a bit of storage as alignment is costly, but probably we have to see how much is lost. As like we said, I think there are structures which are already adding padding and things like that to make this, so it might average out when we have a framework and everything moves into the framework. The implementation would obviously change for the definer and access interface. Interfaces would stay same, but the implementation would change. I did when we start with the presentation, I did talk about single chip not having any change. But if we are to break the array and make it into separate objects of a particular CPU, then we would obviously have to change single chip, and that's why I had those stars marked up to it. But the key point here is this is not a NUMA node or a multi-chip or a multi-chip problem, but it is rather a multi-CPU problem. So even for a system with n number of CPUs, but just one NUMA node, one node, we would still have this problem because multiple CPUs still have local caches and cache ownership can switch between different CPUs. So this is something that is worth doing because we'll have performance benefits to it. Okay, so the other big consumer or the other big the aspect which takes up a lot of space is a stack. Stack is also per CPU, and which means that more CPUs we have, bigger the size the stack would consume in total. Unlike the other context variables, we have stack as of today for trusted firmware is based on a section. This particular section is called TC firmware normal stacks. We have plans to migrate the stack. It would be beneficial to have the stacks also per node so that latency is less. We have a balance in terms of the storage. And this is at a very high level what we would have to do. It's basically removing the stack has a separate section as we talked about. So it has to be removed from the linker script, and then it would be defined by the framework. And whenever we have a SP switch, a stack switch, the access interface has to be used to make sure that it is pointing to the right. It's pointing to the right node stack, right CPU stack, in fact. And these are the interface variants we would have to support, or these are some potential use case I could think about. So we did see the first CPU and the CPU's pointer interface, which gave out a pointer back. It is also beneficial to have a object interface where we can directly work on the object. So something like this for CPU SPM. This is the SPM context, and it's directly acting on the object. So that's something that we can think of. If certain objects require additional alignment, so that it has to be aligned on a 64 or a cache line boundary or any kind of boundary for that case. There could be interfaces which would support that. So yeah, we would also need to take care of this in the linker script to make sure that the sorting is all fine. But the idea is that we can have interfaces to support extra alignment or tighter alignments. Support for array of per CPU objects. So this is an example I have where you have 8-byte shadow registers, 16 of them for a particular CPU. This is also something that could be supported. An interesting use case we could have is, this is something from our current source code where there's a use case where it's using initialized per CPU variables. So this 1 and 2 is showing that we have it initialized. So this is also something we can think about if it's worth adding support for. BL32 has some references to per-CPU objects. So there's platform core count, and this is basic from the BL32 code. So it might be useful to have the support for BL32 also in the future, something that we can think about. One key point is that it is okay if something is not falling into per-CPU framework. So it is not a breaking change in the way that everything has to move into per-CPU framework in one go. If RMM context is not moved in the first instance of having this framework, it is fine. It won't break the build. So we can take it as a long-term activity where we see more crucial objects moved initially, so that there's that performance and storage benefit coming in, and then probably progressively moving the smaller objects as we get more time. So that's all I had in terms of how the framework looks. If we have any questions or other items, we can talk about it now.
I think it's a good proposal. Good work, guys, on this. I think as I mentioned earlier, there's an addition, at least one more hierarchy that would be nice, which would be per node, because in addition to the per CPU structures, there is a value in having a per node offset, because you want to NUMA is not just about localizing things per CPU. It is about localizing things per NUMA node. Have you guys considered I mean, you may not need the TPIDR optimization, which looks like a good optimization, but have you guys considered that as another hook that could be used for certain structures?
What I have a question. So what sort of objects would be falling into these the NUMA nodes? Let's say if it is outside of the per-CPU. Yeah,
it could be, it's going to be platform specific, right? But it could be a peripheral that you might prefer, a localized peripheral. It could be structures that are, you want to place local to that NUMA node, right? And it may I think it's going to be platform specific, and maybe folks can just develop their own APIs, and that's something that folks may already be doing. It just, for over time, we might find some structures are per node structures, and then you can have that framework in place to move those structures into the per node category instead of the per global category, because you're going to find that you have it's going to vary between platforms and industries, I think, and markets, but I do believe there's going to be a per node use case that might be a broader need, and just having that to complete it, just I mean, we've learned that there's already precedent for how you do NUMA, and in higher level software, and this would just complete the full story, where you're covering both the per CPU, like as you stated, what you guys are covering isn't necessarily a NUMA problem. You're trying to localize and bring things closer to CPU, but then there is that other layer, bringing things closer to the memory for a group of CPUs. It's just that second level. Does that make sense?
Yeah, that makes sense. I do get that. I'm thinking this can be done from a platform specific way for sure. You can tie off certain objects to a particular SRAM, but having a framework to have it all fall in different NUMA nodes. I see.
Just to give, if you look at Linux, how they do page tables, for example, you have XLAT as global there. That's the level 1, that's true, but level 2 you could envision optimizing that as well.
Okay.
Am I right in saying that you're always going to get optimal performance by localizing it to the core? That should, in theory, keep it as optimal as possible for the group as well, right? I mean, presuming they share like an L2 cache or something.
n-
Is this where you only have one instance of something for that whole group of nodes? So it becomes less about per CPU and more about per node structures.
Yeah, so this so far what we're covering is you have a per CPU, bringing it closer to CPU, and global. Those are the two categories we have. What I'm proposing is we have a third category, which is there's a structure that I want local to the node, which is how we do NUMA nodes in like high-level operating systems today, right? So, you know, page table is an example of where we do this, right? Where to reduce the cost of a TLB miss, if I could bring my level 2 and level 3 PTEs closer to me, the latency of the page table walk is reduced. So this isn't anything innovative. That's what existing software does with NUMA.
Yeah, I think the issue is in current TFA upstream generic code, we don't have any example of such an object which needs to be shared by a group of CPUs. It's either per CPU or global.
No,
I guess
we have JIC multi-chip code, right?
which one? Sorry.
The JIC multi-chip code.
Yeah, that's the code. Yeah, are we proposing the code also to be node specific?
No, yeah, I mean, JIC is just an example where you have precedent for a per node structure. It's JIC specific code right now. I mean, it's fine. It's just feedback right now. I think this is a good proposal as it is. I'm just pointing out that there's a third category, and
duplicating code and RO is something that we did think about, at least from a platform perspective, but there are some challenges around it. One is that it's a direct map code, so having it in different NUMA, even if you want to duplicate it rather than spreading it across, but it is, since it's code and RO, we have to duplicate it. Since it's direct mapped, it won't work. So we have to have relative branches before MMU is turned on. Then, so those sort of changes have to come in if we want NUMA benefit for at least for the.
No. Yeah, I'm definitely not suggesting that.
Yeah.
I know. If I'm frank, I think there's a lot of research and white papers around code duplication, and there's a whole slew of challenges that come with code duplication.
Yeah.
What I'm simply talking about is there's global structures that could be put into this third category.
Okay.
That's all I'm pointing out, and I think this is a good direction, and if we start here, I think that's a improvement to start with. I'm just pointing out that there's it'd be useful to have a 3-level hierarchy instead of just a 2-level hierarchy. That's all I'm providing as feedback. Does that make sense?
That makes sense. Yes.
You mentioned that there are a few per CPU structures. Is it beneficial to be able to compress several entries from, several, let's say, first entries from multiple per CPU structures into one cache line? So let's say you've got 2 per CPU structures. Can't think of an example.
Yeah.
But entry 0 for one of those and entry 0 for the other of those. Is it ideal to try and keep those both within the same cache line?
Yes, that's what OP2 does. So with optimization 2 coming in, all the per CPU objects for a particular CPU would be clubbed together.
Ah, great. Okay, cool. Thanks.
And they'll be on a cache line bound. Yeah. That is beneficial. Yes. Any more questions?
No more question? Okay. Then, well, thank you, Rohit.
Sure.
for presenting.
Do we have a timeline, or what is what do you guys have some kind of idea of what the timeline is for providing these patch series?
We have not started. Sobi, do you want to go ahead, or I can talk from my perspective?
You can go ahead.
So I did try out a reference implementation to see how much of work this is. I believe it would take a bit of time to have. So the idea is to have, at least like we said, this coming in as series, so that we don't try to move everything in one go. At least few months is what I'm thinking for the first series, to make sure that this doesn't break anything, and what we are planning to do is exactly is what we get out of it. Yeah, I don't have a strict timeline in mind, but this is what I could think of after doing a reference design for this.
Would this land in Neoverse reference design trees first and be upstreamed?
Hoping that's the plan. So at least I'll be trying out with Neoverse platforms first, because that's the platform we work on. And if it's all good, yes, it'll be definitely posted for upstream.
Okay. Was there another question?
Yeah, I mean, the second level question obviously is, well, we're only talking about BL31. RMM and Hafnium would be the second level to this, right? So this isn't a problem unique to BL31, right? So are you guys looking at providing the same, I mean, it could be the exact same type of API and framework for both RMM and Hafnium. Is that something you guys are considering?
Yeah, for RMM, we are considering something. But we are not ready to talk about it yet, but the concepts are similar. So yeah, I would think more or less have for CPU localized objects getting allocated to the local DRAM to that CPU. Yeah.
Well, for Hafnium, I guess it's known at least, but not really engaged in terms of the design, as far as I know. Okay. If no other question, last call. In that case, I will stop the recording.
Yeah, thanks, guys.